It's a quiet Tuesday morning at the Space Telescope Science Institute when Dr. Sarah Chen opens her latest batch of Webb telescope data. She's expecting to see distant galaxies, maybe some early star formation. Instead, she freezes at her computer screen. Scattered across the deepest reaches of space are dozens of tiny red dots that shouldn't exist. These aren't galaxies. They aren't stars. They aren't anything in our cosmic catalog. Within hours, the discovery spreads through the astronomical community like wildfire. Emergency meetings are called. Research papers are put on hold. Because these little red dots are doing something impossible, they're breaking the fundamental laws of physics as we understand them. The Webb telescope, humanity's most powerful eye into the cosmos, has found objects so mysterious that they're forcing scientists to question everything we thought we knew about the early universe. What are these objects, and why do they terrify the world's leading astrophysicists? To understand why this discovery is so revolutionary, we need to grasp just how extraordinary the James Webb Space Telescope really is. This isn't just another telescope, it's a time machine capable of peering back over 13 billion years into the past. When Webb captures light from distant objects, it's literally seeing ancient history. The light from these far-off sources has been traveling through the void for billions of years before reaching us. The farther we look, the further back in time we see. It's like reading pages from the universe's diary, written in the language of starlight. The scientific community had been waiting decades for this moment. Webb was designed to answer some of our most profound questions. How did the first galaxies form? When did the earliest stars ignite? What did the infant universe actually look like? After years of delays and billions of dollars, astronomers finally had their cosmic archaeologist. But here's the thing about scientific discovery. Sometimes, when you think you're about to get answers, the universe throws you a curveball that creates entirely new questions. And these little red dots? They weren't just a curveball. They were like the universe saying, "You think you understand me?" Think again. The discovery happened gradually, then all at once. As astronomers combed through Webb's early deep field observations, targeting the most distant corners of the observable universe, they began noticing something odd. In region after region, scattered like cosmic breadcrumbs, were these peculiar red dots. At first glance, they seemed insignificant, tiny pinpricks of reddish light barely visible even to Webb's sensitive instruments. But as the data poured in, a disturbing pattern emerged. These objects were everywhere in the early universe, yet they looked like nothing astronomers had ever catalogued. These weren't the sprawling, chaotic galaxies you'd expect from the early universe. They were compact, intensely red, and emitting light in ways that defied explanation. Their spectra, essentially their cosmic fingerprints, didn't match anything in the astronomical databases. It was like finding a new species of animal that didn't fit into any known biological category. Word spread quickly through the tight-knit community of cosmologists. Conference calls were arranged. Data was triple-checked. Slowly, a terrifying realization set in. Webb hadn't just found unusual galaxies. It had discovered what might be an entirely new class of cosmic object, one that existed in an era when such things should have been impossible. To understand why these little red dots are breaking physics, imagine finding a fully grown redwood tree in a month-old garden. That's essentially what Webb discovered in the cosmic landscape. The first problem is their age versus their development. These objects appear to be incredibly massive and mature, some containing the equivalent of billions of suns worth of material. But they exist at a time when the universe was only a few 100 million years old. In cosmic terms, that's infancy. The universe simply hadn't existed long enough for normal processes to build such massive structures. Think of it like this. Stars form slowly, galaxies evolve gradually, and supermassive black holes grow by feeding over billions of years. It's a methodical process, like watching a city develop over centuries. But these red dots suggest that somehow, in the cosmic equivalent of just a few months, entire metropolitan areas appeared fully formed. The second issue is even more troubling: their location in space-time. We're seeing these objects at a distance of over 13 billion light-years away, meaning we're observing them as they existed when the universe was in its earliest epochs. This was supposed to be a simple, relatively empty time. Hydrogen gas slowly clumping together, the first stars just beginning to shine. It wasn't supposed to be populated with mysterious massive objects that glow with impossible brightness. The third problem is their light signatures. Every cosmic object has a unique spectral fingerprint. Stars burn in predictable ways. Galaxies emit characteristic combinations of light. Black holes create specific radiation patterns. These red dots don't match any known template. Their light tells a story that doesn't align with our understanding of stellar physics, galactic evolution, or black hole behavior. Multiple independent research teams have verified the observations. The data is solid. The mystery is real. And our current theories simply cannot explain what we're seeing. Enter one of the most mind-bending theories in modern astrophysics. These little red dots might be black hole stars, objects so exotic that until now, they existed only in the realm of theoretical physics. Imagine a star, but instead of being powered by nuclear fusion in its core like our sun, it's powered by a black hole. This isn't science fiction. It's cutting-edge theoretical astrophysics, based on conditions that could have existed in the early universe. Here's how a black hole star might work. In the primordial cosmos, when dark matter was more densely packed and the universe was far more chaotic, certain massive stars could have formed with black holes at their centers. But instead of the black hole immediately consuming the star, something remarkable happens. The black hole feeds on dark matter particles that annihilate around it, releasing tremendous energy. This energy creates outward pressure that actually prevents the star from collapsing entirely. Picture a cosmic tug of war, the black hole's gravity pulling inward, while the energy from dark matter, annihilation, pushes outward. The result is a stable, incredibly bright object that could exist for millions of years, a star with a black hole heart. These could be the universe's first power plants, converting dark matter directly into light through the most efficient engine possible, a black hole. This theory elegantly explains several puzzling features of the red dots. Their incredible brightness? A black hole is far more efficient at converting matter to energy than nuclear fusion. Their compact size? The gravitational forces would keep everything tightly bound. Their strange light signatures? We've never observed a black hole star before, so we wouldn't know what one looks like. The implications are staggering. If confirmed, black hole stars would represent a completely new phase of stellar evolution, one that existed in the early universe but may be impossible to form today. We might be looking at fossils from a cosmic epoch when the laws of physics operated under conditions so extreme that they allowed for the impossible, stars powered by the very objects that usually destroy them. Of course, the black hole star hypothesis isn't the only game in town. The scientific community thrives on healthy skepticism, and several competing theories are battling for supremacy in explaining these cosmic enigmas. The first alternative suggests these might be supermassive black holes that somehow manage to feed far faster than we thought possible. Traditionally, black holes grow slowly, limited by physical processes that prevent them from consuming matter too quickly. But what if the early universe's extreme conditions allowed for rapid, sustained feeding? These could be black holes that broke their own speed limits, gorging themselves on primordial gas at unprecedented rates. Another theory proposes these are exotic early galaxies with completely different formation mechanisms than anything we see today. Perhaps the early universe's higher density and different chemical composition allowed for galaxy formation processes that simply don't exist anymore, like finding traces of an extinct ecosystem. The primordial black hole theory is particularly intriguing. These would be black holes formed not from collapsing stars, but directly from the Big Bang itself, dense regions that collapsed into black holes in the universe's first moments. If true, we might be seeing the universe's original black holes, still active after 13 billion years. Then there's the measurement error hypothesis, the idea that we're misinterpreting the data, perhaps seeing cosmic illusions created by gravitational, lensing, or other effects. While less exciting, it's the kind of careful skepticism that keeps science honest. But here's what makes this mystery even deeper. Most of these objects don't emit the X-ray radiation we'd expect from actively feeding black holes. It's like finding a bonfire that produces no heat, another impossible property that none of the competing theories adequately explain. Among all these mysterious red dots, one object stands out as so extreme that astronomers have given it a nickname that reflects their bewilderment: the cliff object. If the other little red dots were breaking physics, this one was setting physics on fire and dancing on its ashes. The cliff object pushes every impossible property to its absolute limit. It's more massive than it should be, brighter than it has any right to be, and located at a distance that makes its very existence a cosmic paradox. When Dr. Labbé's team first analyzed its properties, the numbers were so extreme they assumed it had to be a computational error. But the error wasn't in the math. It was in our assumptions about what the early universe could produce. The cliff object appears to contain the mass equivalent of dozens of billion suns, compressed into a region smaller than our solar system, existing at a time when the universe was barely 400 million years old. To put this in perspective, that's like finding a fully formed, bustling metropolis on Earth, just 40 million years after the planet formed, when life was still just simple organic molecules. This object has become the ultimate test case for any theory attempting to explain the little red dots. Whatever these objects are, any successful explanation must be able to account for the cliff object's extreme properties. It's not just another data point. It's the universe's way of saying, explain this if you can. If any of these theories prove correct, we're not just updating a few textbook chapters. We're potentially rewriting our entire understanding of cosmic evolution. The implications cascade through virtually every area of astrophysics, like dominoes falling in slow motion. Consider what black hole stars would mean. We'd have to revise our models of early star formation, dark matter behavior, and the timeline of cosmic structure development. The early universe wasn't the simple, gradually evolving place we thought it was. It was a cosmic laboratory, creating objects so exotic we're only discovering them now. Galaxy formation models would need complete overhauls. If massive structures could form this quickly in the early universe, what does that say about the pace of cosmic evolution? Did the universe develop much faster than we believed? Are there entire phases of cosmic history we've missed? The dark matter implications are equally profound. If dark matter could annihilate efficiently enough to power black hole stars, it suggests interactions and properties we haven't yet discovered. We might need to fundamentally reconsider one of the universe's most mysterious components. But perhaps most importantly, this discovery reminds us how much we still don't know. We've been studying the cosmos for centuries, built increasingly sophisticated instruments, developed elegant theories, and then the universe surprises us with something completely unexpected. It's humbling and exhilarating at the same time. These little red dots aren't just challenging our theories, they're challenging our assumption that we understand the universe well enough to predict what we should find when we look deeper into space and further back in time. The discovery of these objects has opened up Pandora's box of cosmic questions that will likely take decades to answer. How many more of these objects are hiding in Webb's data, waiting to be discovered? Can we develop new observational techniques to study them in greater detail? What happened to these objects over cosmic time? Do they still exist today in forms we haven't recognized? Will future space telescopes reveal even stranger objects lurking in the early universe? Are the little red dots connected to other cosmic mysteries we haven't yet linked together? Could they help explain dark matter, dark energy, or the universe's accelerating expansion? Every answer seems to generate 3 new questions, and each new observation adds another layer to the mystery. As we reach the end of our journey into this cosmic mystery, we find ourselves where we started, staring at impossible objects that refuse to fit into our understanding of reality. The little red dots continue to glow in Webb's images, silent witnesses to cosmic processes we're only beginning to comprehend. We're living through one of those rare moments in scientific history when our fundamental assumptions about the universe are being challenged by direct observation. Just as Galileo's telescope revealed moons around Jupiter and forced us to reconsider Earth's place in the cosmos, Webb's little red dots are forcing us to reconsider everything we thought we knew about cosmic evolution. The universe still has secrets. The little red dots might be just the beginning of what we'll discover as we peer deeper into the cosmic abyss. What other impossible objects are waiting in the data, ready to break physics once again?
This is Beyond Revealed. Subscribe now and join us as we explore the mysteries that lie within our world and far beyond.